Good afternoon, everybody. So now we'll have the second lecture of Tobias Frederico.
Okay, so now I will continue our quest of the FADEV equations, just reminding you this structure that is quite intuitive. So this is the FADEV component of the wave function. This is the free resolvent here. And here, the two-body T matrix of the pair JK and the two components. So now, we just introduce here the transition matrix for the contact interaction or separable potential, if you like. That has this structure, reminding these are the form factor, this is the transition matrix, these are the form factor, and in momentum space, this is just a constant. One in this case already, okay? And then introducing this form in the FADEV equation, we can factorize the dependence on the momentum of the third particle from the relative momentum of the other two. So this simplifies a lot, no? The FADEV equation. So we just rewrite the FADEV equations here in terms of this reduced wave function. It's not really a wave function because the wave function you have to rebuild with all these ingredients. And then when you do that, this is the two-body amplitude that in the limit of the zero range interaction is just 1 over k cot delta minus ik. Essentially that on the, where k is just the square root of this. If you are in the bound state region, that is our case, the energy is negative and this quantity is real. Okay, now for three, just going one step more, no? In deriving the Skorniakov and Terma-Tiriosian equation. So this is what we got. Now we have to take into account that this reduced wave function depends on the momentum of particle, no? On the Jacobi momentum of particle I. So suppose A is I, so is this relative momentum QI. Okay? And here, just for convenience, I just use numbers now. So I, 1, 2, 3. Now, for three bosons, of course, this amplitude and this amplitude, as well as these kernels, are identical, unless the transformation of the Jacobi momentum. Okay, so we have this guy is the same, because for this particle, doesn't matter if you look to J or to K, then you have a factor of 2, because two identical bosons, or three identical bosons, and then the same function that comes here enter here. The only point is that here is the momentum with respect, for example, to boson 2, okay? And then we have to take into account that these form factors here are just a constant. We introduce unit resolution in terms of the Jacobi momentum that you see here, no? And then this is the general form. The only point that now needs some attention is the matrix element that corresponds to the change in the basis of the Jacobi momentum. So remember, this is the relative momentum between particles 2 and 3, and this is the Jacobi momentum of the third particle with respect to the center of mass of the other two. That is also the momentum of the particle in the center of mass. Okay, and then the two form factors. Okay? And we have to take into account that we are in the center of mass frame as well. No? Otherwise, we have to factorize the center of mass, but we can work out already in the center of mass frame. And this, when you take into account those transformation between momenta, relative momentum of two particles and the third particles, take into account the condition of the center of mass, you arrive at these two identities. And then you just substitute. Okay, so now I arrive to this equation. Again, I'm calling your attention to this part here that is essentially proportional to the S-wave scattering amplitude. And here I can have either a bound state pole with plus and a virtual state with minus. So you see that if I have plus here, if this quantity is equal to the bound state energy, sorry, I forget a modulus here and minus. So this is the modulus, okay? So I missed it, sorry. So there is a modulus missing here as well as here. Okay, and this is the two-body amplitude, and diagrammatically I write here this equation, so this is the two-body amplitude, and here I have the propagator of this three-particle system in the center of mass, and here the amplitude, and you see the exchange between particle 1 and 2, that's all. So, and here is the resolvent after you introduce the transformation, this transformation between the Jacobi momenta. Okay, so now what is interesting in this equation is this property here. This is now we are on the verge of very interesting physics. If I go to very large momentum, really I messed up the signs here, sorry. I think maybe it was too late when I was typing that. Okay, so here there is a plus, there is a modulus, okay? Then, when this momentum is very large, you can think that as you have E2 equals 0 and E equals 0, because this will give you a factor of 1 over Q. And then the same is valid here. You can throw away this energy. Then what you see an equation that you have 1 over Q, D3Q, 1 over Q squared. There is no dimension, no dimension. Therefore, the solution of that equation is an homogeneous function because a transformation, a scale transformation, do not change the solution. The solution should be invariant under the scale transformation. Therefore, can only be an homogeneous function. I mean, of course, it's a linear equation. You can change a factor. Okay? And now we can look also, in this case, to the S-wave solution, because this is the most, for the physics I want to mention. Okay? You see, for higher wave, I can only say that the observables that comes from this type of equation, for example, in the scattering, the scale is this energy E2. Okay, they scale with that. So you do not have the problem of the scale, of the breaking of this scale invariance for higher partial waves. Okay, so this is the property. This is a simple example, as you can see, that you can solve playing with your mathematics and invent your own homogeneous integral equation that has the same property. Okay, so what we see dp squared, p squared, so this divided by p squared, so no dimension. So this equation bears the same property as the Skorniakov and Terma-Tirios equation. So the solutions, as I mentioned, are of this type, a power law, homogeneous function. No? And then, when you just insert k eta here, you can prove, p to the power eta, by a scale transformation, you got k to power eta. But you have a transcendental equation for lambda. And this is the transcendental equation. It's a very simple game. You can do in Mathematica. You could make any type of these equations that bear this property. They will behave exactly the same. So this is very general. Even in solutions of quantum field problems, you see that. But then what happens? This is lambda, and this is the power, okay? And this is the behavior. But lambda, I can put whatever I like. Why it should be below the lambda critical? That in this case is 2 pi. If you have p squared and take this to the square, you are going to have another critical lambda. And this is the point. In principle, no one forbids you to move this lambda above this critical value. When you do that, you still have a solution, but your power gains an imaginary term. And you have 2 solutions, plus and minus, some number that you can derive. I didn't put the solution, but S naught will be a function of lambda. And then you have 2 possible solutions on equal foot. What you do? You need a boundary condition. Okay, you have to fix. Before, only lambda was enough to fix below critical lambda. But above, I need to introduce physics. And then when you introduce some boundary condition, you can rewrite, if you like, your solution in this form of 1 over k and sinus of S0 log of k star. You need, k star is your physical condition. Now, what happens with this solution? Now you introduce a scale. So you destroy that property of continuous scale invariance. But you keep a discrete scale invariance. And if you change k by this exponential, the solution doesn't change. And this is the discrete scale invariance. This is exactly behind Efimov effect. And other physics that comes with equations that you can complicate this as in the way you want. But this is the main point. You have a continuous scale symmetry that is broken to a discrete one. Okay, now let us go back to Skorniakov intermaterial-Sun equation. This is the solution already done in 1961, okay? Maybe even your parents were not born, many of you, in 1961, but he understood that. And this is, he studied the S-wave. This is the S-wave, Skorniakov intermaterial-Sun equation. In that limit, how we say, ultraviolet limit, where you disregard all the solutions. And you have an homogeneous solution, but in this case, all the factors are fixed. You cannot move. But what happens is that this S gains an imaginary part. You don't need to change anything, okay, just with these factors. If you multiply this by some quantity, of course, you can decrease below the critical coupling, and then you destroy the Efimov effect. And then you introduce one scale. Remember, how do we interpret this scale? This is a Threebody scale. In the beginning, I said, okay, we have the Dirac delta. We have to start to ask how many scales I need to describe, for example, my bosonic system, when the range of the interaction goes to 0. And what we see that when you break the continuous scale invariance to a discrete one, you need to put one scale. Already Danilov recognized that in 1961, but he didn't notice the Efimov effect. No? Came about 10 years later that Efimov noticed that this leads to this infinite number of bound states, but with discrete scale symmetry. Okay, now another example, I just want to, this is a classical example, is the fall to the center that is illustrated in the book of Landau, of quantum mechanics. That is a problem that also you have scale symmetry, just 1 over r squared potential. Then if you go to very short r, of course you can disregard the energy, and then you have scale invariance, because the dimension of the kinetic energy operator is the same as the potential. Of course, we know if this is angular momentum at short distance, I know that the Bessel functions are power law, nothing new. But the interesting thing is that when this coefficient is larger than 1/4, then happens the fall to the center. The system simply collapses. And why it collapses? Because your power gains an imaginary part, and you have the two solutions. Again, you need to introduce a boundary condition. And this is the kind of solution that you have. And then if you think, a very simple example, now you put a boundary condition and solve this elementary problem and take the bound states, you are going to see that the energy of the bound states are separated by a geometric factor. And the geometric factor is exactly the geometric factor that Efimov put forward. This discussion, exactly on that is not in the book of Landau. But this is behind what Efimov did. That's all. And on the other side, when you look to this simple example, as I'm mentioning, you say Efimov is low energy physics, and Thomas effects is, high energy, you are in the ultraviolet. But the point is the scale invariance. When you have a scale invariance, when you start, doesn't matter, it's the same. So the fall to the center at the same time, collapse the same, was discovered by Thomas in 1935 when he was studying the people at that time didn't know that the nucleon-nucleon interaction had some range the people thought could be of contact. And then Thomas proved that if so, the helium-3 or the triton would have binding energy of minus infinity. And then this is the Thomas collapse that if you treat according to Efimov, this will be the fall to the center. It's exactly the same physics. So both phenomena, Efimov effect and the Thomas collapse, are related. Now you can think that if I add angular momentum, depending on the size of this constant k, of course I can destroy the Efimov effect. And this is what we see in 3 dimensions, at least for 3 bosons. We see exactly that. But in extremely mass asymmetric systems, you can have Efimov effect in higher partial waves. Now I will mention this later on. Okay, this is now the famous paper by Efimov of 1997, and he taught this problem in the context at that time in nuclear physics. And then for many years, this was put on the side, because you cannot manipulate the nucleon-nucleon interaction. It's that and finish. And he applied these ideas. He thought about the deuteron weakly bound, the singlet state, the triton. He applied. You can really find some traces of the Efimov physics already in the properties of low energy scattering and of nucleon deuteron or things like that, and the triton. And this is the plot, kind of plot that Efimov did. So this is the inverse of the scattering length. So this is when the scattering length is infinite. So you have states, trimer states condensing. And when you move the scattering length, you go, this is the two-body threshold. So the energy of the trimer is the energy of the diamond. This is why it's a parabola. You can see an inverted parabola. And in this side, you go to the region where your system is Borromean. So the pair is not bound. And this is exactly at this point, when the trimer crosses the zero energy, that the people observed the resonant recombination. And they were able to see this characteristic distance between two resonances that says, oh, this is Efimov physics. So this was indeed studied in this paper by Rudy Grimm and his group back to, I don't remember exactly when it was. but maybe it's more than 10 years, 2009, you know, in a ultra-cold gas of cesium. Okay, now this is just a simple digression about the Thomas collapse, Efimov effect. So a Thomas collapse happens when the range goes to 0, Efimov effect when the scattering length goes to infinity. So this is the route to collapse, and this provides these infinitely many states. But what is relevant is the ratio between the two. No? And this ratio what matters. And this is what we saw in the Skorniakov intermaterial sun equation, that what is important is this ratio, the scattering length to the range going to infinity. Okay? But summarizing, so we now know one Threebody scale is necessary. People that study effective field theories, Bira will talk this next week, this is what they call the Threebody parameter. But you could say in general. Okay, so now it's here. So you have an equation that collapses, so you need to regularize it. And this we did by subtraction. We used the same ideas that I showed. No? So this equation here is the regulator parameter, is some scale, and everything is measured with respect to this scale. So you have epsilon 2, so energy are measured in units of this short range scale. And of course, then you can immediately see what is the Efimov effect. Epsilon 2 goes to 0. And what is the Thomas collapse? Epsilon 2 goes to 0 because the dimer energy, no, could go, epsilon 2 could go to 0 for a fixed dimer energy, and this short range scale going to infinity. Okay, so now we unify it. Now we have to explore this equation. Just to let you know, this is the wave function and cyclic permutation. So if you apply here the free Hamiltonian, this is an eigenstate of the free Hamiltonian. And of course, all the physics is buried. You see here the scattered wave. Remember that picture that I presented in the beginning. So this is the circular wave that you have. Of course, for the bound state, this will be just a damped wave. And here is this reduced wave function. Okay, so now when you play this game, you change epsilon 2 to 0. So this is the threshold. So states start to appear from the threshold. So when you go to 0. And then at some point, another state. Then at some point, another state. The ratio of these points follow a geometrical ratio. And then you could ask, and these functions, they are self-similar. Now we are going to talk about the limit cycle. Okay? You can also ask, but what happens when your epsilon 2 is not in the point that this Efimov trimer appears? Where is this Efimov trimer? It is a virtual state. This was discovered long ago by Lauro Tomio, Adhikari, Fonseca. Yes, I think I mentioned here. Okay, so now we see that there are limit cycles. So there are scaling laws, no? And this is the way we see the physics. We don't put a Threebody parameter, but we correlate observables to observables. So now the energy, you could say, in that Skorniakov intermaterial sun regulated equation, that the energy is a universal function of this epsilon 2. This is dimensionless, no? And then, of course, I can rewrite this guy in terms of dimensional quantities, okay? Now, I can write the ratio between two bound states. If epsilon 2 is equal 0, I know this is just the Efimov factor. But when you move that, what will happen? If I start to compute that and make n big, so this converge to a limit cycle. So this is the limit cycle of the observable. No? And they are separated by ratios of 22.7 or 515, depending on what the units of the observables you are looking. Okay? So it manifests like that. And you could say, you can compute this function. It's very easy. You can compute. Is that has something to do with with the physics, with reality, amazing? The answer is yes. So you see, this is that function. So this is the region where the trimer goes to a virtual state. This is bound. And this is the region when the scattering length is negative, and you go to a resonance. I will mention that. You know, you see this little point. So this is the ratio between the excited state minus the dimer state divided by the state below as a function of the dimer energy divided by the scattering, the trimer energy. So this is a limit cycle. You can, normally with this kind of equation, you compute 1, 2 cycles, it converges, no, for this type of equations. And this red dot is exactly what the people measure for the helium trimer. The ground excited state is on the top. And all these points are calculations done with potentials, different potential. I have a whole potentials that mixture D waves and whatever, but you see, you can really characterize the limit cycle. But the potentials are of short range. Okay, so this is the F-mob state trajectory. So when you change epsilon 2, so your trimer, if you decrease epsilon 2, no? If you increase epsilon 2, your collapsed Thomas state or F-mob state, they comes to the threshold, to the two-body cut, we say. So here is the dimer energy. And then what happens? This state, when you have not a Borromean since, but the dimer is bound, as I mentioned, it becomes a virtual three-body state. This was really discovered quite a time ago, no? And we have also explored that in the context of Skorniakov and Termatilios equation. You can do this for the Triton. The Triton has a virtual state, indeed, our Triton, no? Lauro have computed that. And now when you go to the Borromean side, negative scattering length, okay, what happens with this state is that this state dives into the continuum, is a resonance. And you can see this is more or less, I just sketched here the trajectory. And then, of course, as the energy, you see here, the position of the resonance increase, your scattering length in modulus decrease. And people have observed that. So this is what we see in this experiment by Kramer. And these are the peak of the three-body resonance with different temperatures. And then when they increase the temperature, the position of the peak moves to modulus of the scattering length decreasing. This is exactly what we see here. We can even, essentially be able to find the position of the resonance using, with temperature in this case, no? Using the calculation of the position of that resonance, plus something else. Okay, so now range correction. So this is work part done here, the big part done here by Lucas, no? Because you could say, oh, what about the range? And then you could say, okay, maybe there is some range. I mean, the forces we have already have some effective range. And the K cot delta should receive, even at low momentum, receive some contributions. Now, what we think about these scaling functions? Now we compute the ground state. Can we see only having the ground state energy? Of course, we need a reference. And this, in this case, when we tune, for example, we take a potential, Gaussian potential, or another potential, short range. We tune the strength of the potential to give you scattering length infinite, we are always able. But the range is there. We cannot kill the range of the potential because it's there. So we thought, okay, let us study and see how much universal is this kind of, let us say, scaling function, no? And indeed, we have never done even correcting the Skorniakov and Termatilios, we never looked into this problem. So there is this two-dimensional variable with scattering length, the energy The unitarity, scattering length infinity, and the range is also a dimensionless quantity. So remembering that the two-bodies scattering amplitude just have the scattering length, the effective range, and the effective range really give you an idea of the range is positive. Okay, so now people have already looked to this problem, at least when the range goes to 0. So people have computed this derivative, our group and other groups, and this is a universal number. So this is the first term of that function f of x, is this number 2.11 times x. Okay, but what else? Okay, people, I mean, if you look to this physics report of Bratt and Hammond, they have already parameterized that correlation in these terms, but for effective range 0. And you see here the Efimov exponential that is part of that. No? Okay, so we just look to that dependence. First, just correcting this Korniakov and Terma-Tiriozan, remember that is regulated, then by expanding the scattering amplitude to first order in the effective range. And amazing, this subtraction is enough to render finite. So I have not approved to that, but in practice, we found it. And you see these curves, we are able to compute for different x that corresponds. This is the unitary limit, so this is for different x. And this is indeed a result for many cycles. We are able to compute many, many cycles. And then we parameterize this function. Now you say, okay, very beautiful, but this is only valid to Skornakov and Terma-Tiriozan equation? No. Quantum Monte Carlo calculations with Gaussian Potch-Stellar potential gives, at least for small ranges that we had assessed, gives a pretty reasonable. You see, you could say, oh, this is just a quantum, but there is some, you can see exactly those behavior of these functions. Then, but how you move here, because you need to move, this is a relative to the trimer energy, so there is a repulsive Threebody force that is manipulated, I mean, theoretically. And this really we can see, with quite sophisticated calculations. Okay, now mass imbalanced systems. I'll just be very brief. So this is an example. This is also seen in traps. For example, people, Heidelberg group have seen no mixture of lithium, cesium. And indeed, when you have, for example, two heavy and one light, you can have that the Efimov states are very close. And this is not hard to understand, because it's like you are exchanging a photon between two particles, because it's very light. And this gives rise to this long range potential. Not 1 over r like Coulomb, but 1 over r squared. And this is indeed, and then if you have two heavy and one light, you can really see Efimov states much closer, not 500, but factors of 20 or even less. Okay, and the scaling functions, you can also construct, if you like. And then one particular one that we look is the critical condition to bind an excited state. So what that means, that I have a Threebody bound state of this kind of molecule or halonuclear, whatever, and then I ask the conditions to have an excited state. And so this is 0, or no, or is equal if you are in the region that the subsystem is bound. This is the two-body energy. You can solve this equation. And this is the kind of plot. I just put here for fun the name. So this is the Borromean region. The two scattering lengths are negative, so virtual states. Here one is negative, and two of them are positive. So this is NC bound, so we call it this samba, then now bound and tango. And you see, I mean, maybe carbon-20 could have, but this is not a perfect, halonuclear. So this carbon-22 is here, lithium-11 is here. So this is outside this region. This is the Efimov point, exactly in the middle. You can go to atomic physics, and you see that there are candidates. You see, of course, the helium-4 trimer, that is, even the excited state was measured. This is exactly here. And then you have other systems, helium-4, dimer of helium-4 and lithium-7, the helium-4 sodium is somewhere here, and so on. So you can, for cold atoms, you could have, even in traps, if you are able to have scattering lengths that allow you to cross these boundaries. So this is the Borromean region, for example. Okay, so now you can, for example, see the Efimov factors, you can compute. So this is a paper that we wrote a couple of years ago, just generalization of Danilov method to AAB system at unitarity, and then you are able to get the exponential factor. And this dashed line is for the case when the two heavy are not bound. But you can see here that the geometric ratio between the two Efimov states is in the case of cesium, lithium, is as small as 25, sorry. And this is what was observed by the Heidelberg group. Also, you can look to the wave function. This is the one-body momentum distribution. They also fall defines limit cycles. You see the points, ground, first, second, everything coming one on the top of the other. Okay, so now I will talk about van der Waals universality. What that means? Okay, in reality, when you put the atoms in the trap, the cold atom, they have an interaction. When you go to the short ranges, van der Waals type or no, for the neutral atoms is of this type. And you can manipulate the scattering length because these atoms are in a Feshbach resonance. You have two states. Okay, and there are situations where indeed the physics of these systems, besides changing the scattering length, is dominated by the open channel. Remember that in Feshbach resonance, you have a closed and an open channel. The open channel, essentially, the interaction is through, van der Waals forces. No, and then what the people observed, no? So this is where the state cross, remember the three-body resonant recombination, where you lose the atoms. You see there are distant, this is for identical atoms, that is the case here, so three bosons. And then the people saw that the position where there is this scattering length in this region, the position of the first one, of the first peak, namely for the scattering length, that is the smallest one, is about 9, minus 9, the van der Waals length. Remember, the van der Waals length is that distance that I put it in the beginning, no, where you have the repulsion starting. And then here is the helium-4, lithium, lithium-6, potassium, rubidium, and so on. And then people say, okay, so your short-range physics is driven by the van der Waals length. But this happens for states. This was challenge, and we can understand. This is very nice. It's from, that is in this report, Progress. This was Naidoo and Endo, and they were behind these discussions of van der Waals universality. And then this happens because for example, if you take the Lennard-Jones potential, you have a very huge repulsion. And then the wave function is simply dumped in this region, below the van der Waals length. So this gives you a natural scale. You have only to compute. But even people observed that with very deep potentials. And this is a good point to think about quantum mechanics. Because if you have a very deep potential with many states below, remember that your zero energy solution should be orthogonal to those very deep states. And this gives you the wave function. This you can see when you have a depression, a very huge depression in the sea, that you have the reflection of the wave. So this, this was essentially very detailed study by Naidoo, Endo, and a senior guy that now I'm missing the name. Okay, but people, more recently, couple of years ago, discovered that this is not so. That is violation of the van der Waals universality. And this happens when you have narrow fetch-bar resonance. So this means that the open channel and closed channel are strongly coupled. So you cannot simply forget that it's just the change in the scattering length. It's more than that. And then they really see this is the log of the position against the theoretical one. The theoretical one computed with the van der Waals length. And why? So there is a lot of discussion. And I think this is starting to be understood. Okay, so my general statement that I believe, I will discuss this point of view, that can be an explanation for that. When you have coupled channels, you can have many body forces. If you have many body forces, they can drive your physics. No? This you can play. You can put a two-body potential, a three-body force, and then you can play with the properties of your system, even keeping the scattering length fixed or all the properties of the two-body system. So there are many body forces. And then how do we see it? It's very easy. You suppose you have an open channel. Your particles interact. And then you go to the closed channel. And then your particles interact again and go to the open channel. So from the point of view of the open channel, what is that? A three-body force. Do we control it? No. I think there is a lot of things to think in the future. So we have looked to this problem. I will sketch very briefly how this was a contribution to Hussein volume. So it was really a kind of essay, and not really. But the idea is the following. So we took, just to illustrate this idea, we took an AAB system where AA have open and closed channels. A and B, just one open channel. To simplify, otherwise you start to have many coupled equations. Just to illustrate how those Korniakov and Terre-Material-Sun equations can be changed. No? So this is just the two-body T matrix in the channel AA, that you have two coupled channels, and then you can solve this. You can use the subtracted Green's function, and this is the eta, is just coupling between the open and closed channel, and we put here another parameter. And of course, this kind of T matrix, or scattering amplitude, can give you scattering length infinity, even if the interaction is zero in the open channel. Okay, you can solve that. And for example, for the open channel, you have your K cot delta in this form that I wrote here in a way to allow the scattering length for the AA system to be infinite. And then I can even eliminate one factor, just to simplify. And then you can see here a very nice characteristic of this kind of physics is that you have, of course, this is the E is the separation energy between the open and closed channel, so you have a gap. And when you expand this expression for small p, of course, the first term, 1 minus A, is 0. Then you have the effective range, the second term. This is when p squared goes to 0. And look, this is negative. This was already observed by Petrov. And indeed, if you look to the scattering, if you have seen some fetch-bar resonance, you can see regions of positive and negative effective ranges. And this coupled channel just give you that. Okay, so now these are the equations we have. So we have already altogether 4 equations. Why? Because 4 coupled equations. So because we can put the channel AA in the open channel, that I denote by 0, or in the closed channel, 1. So we have all this coupling. No? And of course, I have one reduced wave function more because AA is different from AB. But here, for simplicity, I assumed the same mass. Even, I mean, this is just to have some idea on how this three-body force can arise. And then you can immediately see, you see here I have 1 going to 0, so closed to open channel. So you see this contribution that I do not have if there is no coupling. And then this equation with this equation are the traditional equation that I already wrote. I passed it very fast, but this is the equation. So you see that you couple, I mean, all these equations, and of course, this will impact. Suppose I calculate now the energy of this trimmer state. I can move it, for example, changing the separation between the open and closed channel. So these are coupled equations. Of course, you could think, but where is the three-body force? The way we could do is to eliminate. Of course, this formally is not easy, but we could eliminate, for example, you see F1 here. Is this coupling here that brings to the physics of the open channel the coupling between the open and closed channel. So I could rewrite, eventually, inverting those equations, F1 in terms of F0 and F0b. This will be really a three-body kernel. What are the characteristics? Okay, we have to think more and more. And another aspect of this kind of equation, they are regulated in order to avoid the Thomas collapse. And we have to understand that this short-range parameters is more or less of the order of the van der Waals length. That, I mean, this type of scale is normally much larger than the separation gap. So we really see that maybe this three-body force can be driven, but thoughts have to be taken, and eventually this could have a hint on that behavior that was found by Shin group. Okay, dimensional reduction. Maybe I will need 5 minutes more, okay? Because I want to talk about that. So D2, 3 to 2, okay? In 2 dimensions, there is no Efimov effect. This was already studied, I mean, many, many years ago. When you have 3 bosons, you have only 2 bound states, and their energies are proportional to the dimer energy, that is the single scale. If you turn this energy to 0, the 2 energies are going to 0. So physics is completely different from the Efimov physics. Why is that? Because you break the scale invariance. You do not for a discrete one. There is no scale invariance in this kind of equation. And I will illustrate that. And we have studied this reduction in 2 ways, because what is the path? We don't know if people have seen or are able to simulate, but we studied this in 2 ways. Compactifying 1 dimension, that is more close. Someone asked me about the harmonic oscillator, to put an harmonic oscillator in 1 direction. And the other one is more inspired by quantum field. We change the dimension of the equations. Okay? So here is the compactification. So now for the 2 bodies, so 1 direction, we just input periodic boundary conditions, and when Rz goes to 0, you remember, you are able to have Pz equals 0. Then you vanish 1 direction. So you have no kinetic energy in that direction. And then what is the scattering amplitude? Before, remember that we had integral, an integration over d3p. Now I have a sum over these modes. And you can solve that to see the 2-body amplitude, and this is the 2-body amplitude. It seems that has nothing to do with what we have seen. But if you make the limit of Rz to 0, you get the two-body amplitude that you'll be able to throw away this guy, put n equals 0, and solve this little problem. And you see here, why in two dimension you do not have the scale symmetry? Because you are not able to throw away this energy. No? So everything is are scaled by the two-body energy. No? Now, when you make Rz goes to infinity, we go to the standard formula. So really, this makes the transition. Okay, you can build the Skorniakov intermaterials with these periodic boundary conditions. And there is one interesting thing that we checked. If we put an harmonic oscillator in one direction and squeeze a two-body system with a given dimer energy, no? Where really we are able to parameterize the two-body energy, because when you squeeze, what happens is that the dimer energy increases like crazy. For the zero-range potential tends towards infinity, but this makes no sense, no? And we are able to parameterize the two-body energy here is in a way that reproduces the behavior that you got when you squeeze a potential, a Gaussian. We tried with a Gaussian potential and a harmonic oscillator in one direction. And this is the kind of formula. A little change on this expression, you can change, you can follow the dimer energy. And for when it goes to 0, this is the oscillator length, you go to some value. And when it is infinity, go to the trimer energy. And these are the kind of plots. So we have chosen the same ratio of lithium and cesium, of masses. So these are 2 heavy and 1 light. And we choose a situation that we have 5 Efimov states. Now, when we start to squeeze the system, first look to the dashed ones. You see that at some point, these states goes to the energy of the dimer. You see, they are going to 1 here. And then one by one are disappearing until only 3 of them are kept. That are the ones that this system have in 2D. Now, this other curve is just when we move the two-body energies according to this expression. So we have some softening behavior. And this is calibrated to this is the oscillator length divided by the 3-dimensional scattering length. So this, we also made, we made more. We changed really the dimension. And so this, I think, is more subtle, how to connect with an actual experiment. But eventually, when you squeeze your trap, if you are measuring resonances between the distance between the resonances, can give you a hint on the effective dimension of your system. Now, the last topic, I will just flash because I see that my time is almost over, is you may ask, okay, very beautiful, Threebody, there is a lot of physics and maybe there is still physics to be learned, no? Not only from maybe from the theory point of view, but from the experimental point of view. But what happens when we start to increase the number of particles? We need more scales when we are in the limit of zero range. Our answer to this problem is yes. And these are the kind of coupled equations. I will not enter in detail, but just very briefly explain. So we have coupled equation for 4 bosons, and then we have to regulate, otherwise this collapse. People sometimes regulate this kind of problem, putting a repulsive three-body force. We didn't do that. We follow our subtraction scheme. And here, if you look attentively, I mean, if you're careful to this term, so this is exactly the part that fixes your trimer energy. But you still have to regulate the other propagations that you have in your the virtual propagation. So, in principle, you are allowed to introduce a new scale. We checked what happens numerically. And curiously enough, so this is the tetramer energy, binding energy, of the n+1 state, minus the trimer energy divided by the state immediately below. We saw exactly the same type of curve that I showed to you, that the helium trimer was on the top. And we computed the first and the second and the third, everything goes on the top of the order. So we conclude this is a limit cycle. We had no proof. Oh, this was done a decade ago. Okay, so we looked at, again, this problem in the Bohr-Oppenheimer approximation. So too heavy and many light particles, many light bosons. So what happens? This is the Born-Oppenheimer equation for the heavy particle. And then essentially, when we increase the number of light particles, the strength of the 1/r² potential just scale. And this factor here that people would say is the Efimov factor, no, it's not. Depends on the number of particles. And even if you have angular momentum between these guys. So therefore, for any new particle you add, any new boson you add to this system, you have a new limit cycle. Okay, then we look at this problem just to see, okay, scale invariance, there should be in these equations, and it should be broken to a discrete one. But the equations, as you see, are quite complicated and depend on two variables. Okay, I have a third particle, a fourth particle, so instead of one variable, I have two. And then, if you look to this equation, you can easily prove that there is a scale invariance. If this is already using energy equals 0. Now, it should be broken. But to prove it, we are only able to sketch it very approximately. Okay, we propose, and then what we found? We do the same exercise as Danilov. We found a transcendental equation for the exponent. So this eta is the exponent. And then you see the first term is exactly the Efimov equation. And there is a correction that we can solve. This is a very, very simple thing that we did. And more or less, when we solve it, you see we got the imaginary part that should correspond to the new geometric scale. This is the kind of solutions we have. And we compare it to our numbers. Okay, it's not perfect. You see, if we take from that calculations, this number, we are able to, more or less. Okay? Remember that the Efimov factor is 1.004 or something. So this is our understanding at this moment, and maybe this can be taken to many more particles. Okay, thank you.
Tobias, questions?
Okay, perfect. This is the type we are not able to answer, probably.
Okay. I saw talks about Efimov physics, many. And everybody involved in this is nuclear physicists from the beginning. Where in nuclear effects, three-body type of bound states make a difference?
In which type of nuclei?
No, where in nuclear effect? I think
yes.
you spoke
no,
about
no,
how long
I didn't
nuclei...
put, no, people have observed many effects of the Efimov physics, but they didn't understood at that time. One of them
in nuclear physics.
In nuclear physics,
Yeah.
I can tell you. And this is where also I was introduced to this problem many years ago.
Because you're a nuclear physicist.
Of course. I am nuclear physics. Then I drive to this direction. But that appears in many parts. So I did, without mentioning halo nuclei, that people believe that...
that's the example you won't give it to us.
But the beginning of this idea. Around the 90s, in the beginning of the 60s, there was a debate about the neutron-deuteron scattering length in the singlet state, spin state. No, they are because it was small and people have hard time. They were able to measure it well in the quartet state. So the deuteron and the 3/2 state, spin 3/2 state. No, when our spins are aligned, they were able, the scattering length is about the neutron proton scattering length. So there was a debate. Then a guy from England, his name was Phillips, not Bill Phillips, another Phillips.
Well, there are many Phillips.
Yeah, many Phillips. So he noted, then he started, okay, so we need theory to try to solve. I mean, what they have two sets of scattering length, and they have to solve. No, for the doublet scattering length, doublet, no, spin 1/2. Then, okay, I want to call the attention that this channel is the same of the triton, where this Femoral physics may apply. Then he noticed the following thing. He took, at that time, they were able to do calculation with simple potential, separable potentials, 1, 2 terms. This was, I think, 1969, if I'm not wrong. And then he noticed that there was a universal correlation between the scattering length and the triton binding energy. I said, okay, I know the triton binding energy, and I get the scattering length. But it's not the same correlation that you have from a shallow state, like the dimer. You could say, oh, this is obvious. No, it's not that. No? And then he made many calculations, and then in this way, he was able to solve, I mean, to say, no, is this set where the scattering length, I don't remember the number, is small. And then later on, more experiments solved that. What is this correlation? Around the beginning of 80s, Efimov explained it. Okay, it's just one of these limit cycles.
Can I have one more question? I have another question.
So this is, I mean,
okay, no, I understand.
the key
that
point.
Is linked to some fundamental interpretation
Yeah,
of
was
the
Efimov.
scattering in nuclear physics.
Yeah.
Okay, well, that makes sense. Now, second question. In my course of quantum mechanics last year, I was taking class, and the professor said that always I have two atoms together. I have more than the bound states. I have rotational and vibrational levels. And when I see the talks about Efimov, maybe everything is included, but what I see is a plot of energy, the inverse of the scattering length, and then the first Efimov trimer, the second,
And so on.
and so it means that we can have a lot of energy in that bound. The first is lowering energy.
Yeah, it's very bound.
So rotation and vibration doesn't make any sense here.
We think about total angular momentum. And in this case, the Efimov states are zero angular momentum. If you go to three bosons, the equation, the centrifugal barrier is strong enough to break up, not to allow a bound state. But I remember, I never published that, but just to tell you, you can find virtual states. But this virtual state scales the position with the dimer energy. So even you can prove that in different ways. But when you go now to very asymmetric systems, like you have in your laboratory, asymmetric mass, so two heavy and one very light, you can have Efimov states, with a lot of angular momentum.
Okay. Now, just one last. Suppose that I have those states may be stable, right? You didn't speak about stability, but they are stable. I make a trimer there, and
yes,
they don't blow away very.
No, but okay. In principle, there is no interaction that made them decay, but continue in principle.
But let's suppose imaginary sample. You know.
Yeah.
Let's now be all theoretician. We have this imaginary sample, and well, it's dense enough, and I tune my scattering length in a good position. And then I have a lot of trimers, Efimov trimer. in the
Suppose you
song.
have a lot.
Yeah, but I still have my other system there,
Yeah.
right? My atoms and everything. And I think the trimer interacts differently with the atoms than among themselves.
Interacts different. I didn't understand.
No,
that.
I
But
want to have
just pull down 1 second, yeah, because
Okay,
I'm not.
I want to have a fictitious sample
Okay.
where I have a lot of trimers in my sample.
Okay. In your
But I
sample.
still have the single atoms around, you
Yeah,
know,
okay.
because I just need the atoms cold enough to do. People
Yeah.
do that not
Yeah,
on condensates. They can
Yeah.
do in very
Yeah,
good samples.
by resonant,
Good.
association,
Yeah.
whatever. Yeah.
Yeah.
So you can have a
The
gas of
trimer
atoms.
interacts among themselves,
Yes, of
and
course.
they interact with the atoms.
with
Single atoms.
the atoms and with the dimers, if you have.
It's possible to have a phase separation in my fictitious sample because I have a kind of enthalpy, and then I have two species.
You say physically separated.
Yeah.
Oh, if you think about condensation, yes, I think, no? So they are going to condense. But the point is that how strongly they will interact. We can say that, for example, the dimer, suppose more simple thing, the dimer and the atom. So if you have the dimer very shallow, this is a very long range interaction, and this will be important, for sure, no, in the interaction. And the kind of interaction, grossly, that you can have, I mean, when you are close to this situation of very large scattering length, is potentials of the type 1 over R squared. Even, I remember now, there are papers by Laura and by myself, I mean, many years ago, where we fit the neutron-deuteron phase shifts, for example, in the doublet state where the triton is, with a potential 1 over R squared. You can play this game. And really, you see that this kind of potential allow you, I mean, there will be an interaction that is of much longer range than the individual interaction, this induced interaction. And then you can understand why. Because you have the two atoms have a large scattering length or for a huge dimer, and of course, the third particle will see something big. And this is of the type of 1 over R squared. So maybe this has to be, I mean, we cannot think about a non-interacting gas. Of course, depends on the density as well, no? But maybe this could well be, for example, at least for a dimer and an atom, that we know more or less for low energy is 1 over R squared. I mean, if you are not able to break the dimer, no? This is, so, I don't know, you have to start to think about, we heard today about 1 over R to the n interactions, maybe, why not? But I cannot tell you what will happen exactly. I mean, this. But the interaction will be there. We cannot treat as a free problem.
More questions? So Tobias, for me, even today, the Efimov effect is very counterintuitive.
Please, I'm not understanding well with these things.
For me, even today, the Efimov effect is very counterintuitive. And I imagine that some of the students seeing this for the first time might also think that, like this. Because you have two bosons that you put them together in free space, they have zero energy.
Bound state energy. Yeah.
They're bound, but
You are thinking interacting bosons?
Yes.
Yes, okay.
they're in a bound state, but with a very,
Very huge.
yeah. Then you put a third one that's like the other two, and if you think 0 plus 0 plus 0 equals 0, no, the Efimov effect tells you equals infinity, minus infinity.
Yeah, you have the ground state of this trimer.
Could you give them some intuition?
Yes,
some
I
physical
can,
intuition
more than
on
that.
why that happens?
One of them I gave, I expect you that you go to Landau and think about this fall to the center. This is the first point, but this essentially is a two-body problem. Now, why you expect this long-range potential to appear. First is the scale symmetry, but this is a mathematical reason. But that simple problem that I showed has scale symmetry. And if the potential is strong enough, it breaks to a discrete one. So the key point is how to visualize this long-range potential that allows that. And very naively, you already gave the solution. We think of something very big, no? A dimer that is very big. No? Then a third particle, when pass by, you see this guy can even pass in between, very far from the range of the other two. Remember the first picture, I put some waves. So this guy is receiving the waves, I mean, from these two guys that are far away, no? I mean, even if they are not on the top of the potential. But the main thing is that you have this big state. When you come with the third particle, you have this guy interacting with this and that. And then this forms this long-range interaction. The form, and then you can use the form 1 over r squared is because scale symmetry. Why there is a scale symmetry? If you have the three particles, I mean, unless they are almost on the top of the other, I mean, this wave function is solution of the free Schrödinger equation. Free Schrödinger equation, as I mentioned, has a scale symmetry. So the only possibility, if you formulate this problem well, is 1 over r squared potential. Of course, this is not the way Efimov did. No, he used boundary condition, hyperspherical coordinates, but physically, this is what is behind. Now, another ingredient that I mentioned here that I think is good to say again is we have two heavy and one light. And this heavy light, no, it has also a very shallow bound state, so they are very long. So that means that this guy can interact with this guy, the light one, at a very large distance because you have the wave function. No, you don't need to be in the potential. I mean, this is correlation. Let us put these two particles, heavy and the light, are correlated by the wave function. And as well as this one. So you have two big things interacting with that. Therefore, these two guys are interacting in the very long range. So I would say that this does not imply that the potential is 1 over r squared. Then you have to take the idea that this huge wave function is an eigenstate of the free Schrödinger equation. Then it has scale symmetry. Of course, you could be more sophisticated and decompose in hyperspherical coordinates and so on. But this is the physics. And of course, then the jump from this situation to the Efimov now is the breaking of the continuous scale symmetry to a discrete one. Of course, this does not say that it should happen there, because we need to be above the critical strength. Then is the detail. But this is the general idea, why you can have so many states. No?
Any more questions?
Weakly bound.
Any more questions?
Hi, Tobias.
Oi.
Thank you. I have one question about the 3D, 2D crossover. So the graph you showed.
I will ask you kindly that put really
sorry.
this noise of the mask, I cannot understand.
I have a question about the 3D, 2D crossover, the
okay.
graph you showed with the energies that are being modified once you start to compress.
Okay, let me go there.
So in terms of
This
the
way.
Efimov effect, you don't expect a sharp transition between a 3D and a 2D system. It will be something
No, what will
continuous?
happen? No. I would say, I mean, in this picture, you see that the Efimov states are disappearing one by one until that state remains only the ones that in 2D are allowed by this zero range potential. And this is exactly what we see. No? So I expect, as you squeeze your trap, some mechanism more soft like that could be in place. Of course, how you could, this is, I mean, for the bound side, because You are not in the Borromean side, but for the bound side, maybe radio association, if you are able to see forming the trimers as you squeeze and you measure, squeeze, measure, but staying in the same, let us say, potential, I mean, in this flashback. And then maybe you can see this. This sharp one that you are asking is when I fix that I think in an actual trap, maybe it's very different. I fix the dimer energy. So you should, at the time you squeeze, you should move the button of the Feshbach resonance to keep it. This is why we made this kind of simulation, I mean, trying to understand the behavior of the two-body problem in squeezed in one direction.
So in a real experiment, for example, do you think we could see this shift on the energy levels of the Efimov states?
I believe maybe one thing that, but is when there is the disappearance of this state. Because when you have an state at zero energy, in this case, you should have a resonant collision of the atom and the dimer. And this is what Vanderlei was asking. Yeah, maybe if you have a resonant collision, maybe you can make that trapped dimer, I mean, very shallow one, to go deep, and then maybe there will be a loss in the trap. No, I don't know. Maybe it's better to try to see this. But you need to have to start your experiment with a couple of levels to be sure. No, maybe, I don't know if you can do this resonant association. What's the name of the guy? One guy from Germany introduced this technique of resonant association. So he can form, you tune your radio frequency at the energy of the trimer, and then you form the trimers, or dimers. But maybe if you have atom and dimers there still, you can see this passage here, no? In the other way, I mean, it will be very nice if you are able to explode. I mean, like I mentioned to you, that we have this effective dimension. If you have your trimer in the trap, if you are able to measure the momentum distribution, it would be very nice to see. And this indeed we wrote not in this paper, but in the next one that is on the archive, that there is a change from the log periodicity of the wave function to something that is not this, that is simple log. And then maybe if you are able to measure some momentum distribution, I know that people have measured things like the contacts that have to do with the tail of the wave function in the traps. So this could be as well. But these are very different methods. We are really exploring those ideas, but would be wonderful if there will be some data to follow that. And even to look at three-body forces in the traps, I don't know, all that. No.
Okay, thank you.
Any more questions? So if not, let's thank Tobias again.
Obrigado. Ok. Agora preciso da aguinha.
And now we go for the coffee break.
Vamos lá.